I'm David Bonsack, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes speaker bios and additional file downloads. If you need help at any time, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our guest speaker today is Professor Randy Ewoldt of the University of Illinois at Urbana-Champaign. Professor Ewoldt is an Associate Professor of Mechanical Engineering at UIUC, where his research group studies rheology, fluid mechanics, and design of complex fluids. In particular, the group focuses on yield stress fluids, polymer gels, biological materials, and large amplitude oscillatory shear, or LAOS, characterization. Randy received his PhD and master's degrees from MIT and his bachelor's from Iowa State, all in mechanical engineering, and before coming to Illinois, held a postdoctoral appointment at the University of Minnesota. Randy's work has been recognized by Young Investigator Awards from the National Science Foundation, the American Society of Mechanical Engineers, 3M, DuPont, and the Society of Rheology. We are very fortunate to have Randy with us today. He's a brilliant scientist, a gifted instructor, and an engaging speaker. The title of his talk is Experimental Challenges of Shear Rheology, or How to Avoid Bad Data. Randy?
Thanks, David. Thanks, everybody, for joining today. This is a fun topic. Anybody who's tried to measure rheology data knows that it's not easy to get good data, and you might even find it joyful to look through the literature to find other people's bad data, to critique them. Today I'm going to be showing you lots of bad data. It's only my own bad data, but it's a good representation to show you some ways of limits of rheology and why it's difficult, when to avoid sharing data that's not actually true in many case studies along the way. So everything that I'm talking about today, the larger portion of it, is documented in a recent book chapter that I had the pleasure of writing, and so I'll point you to that. It's called Experimental Challenges of Shear Rheology, and they let me put as the subtitle, How to Avoid Bad Data, which I'm very glad for, and that's the whole idea today. There are other places to go to learn about avoiding bad data. One of these great resources is the textbook by Chris McCosco, one of the famous handbooks and reference books that I've seen around people's rheometers, is to grab this textbook, open up to the geometry that you're using, look at all of the equations that describe what's happening, and it also describes when the data may not be perfect and non-ideal effects that can happen. In addition to textbooks, of course, you can talk to your other local rheology experts that you may know, but you can also look online. You're online right now watching this webinar, but there are also many other resources online from various rheometer manufacturers and other folks who put things up on YouTube and other online resources. So this is certainly not the one and only, but I'd like to gather things in a particular way today and give us some very good tools for avoiding the bad data that we know may be there. Here's the outline for our discussion. First, I want to show you how bad could it be and give you some examples of when the data looks like it's good, but maybe is not. After that, we'll have a brief discussion about what it is we're trying to measure in the first place and how we're making those measurements. And then the bulk of the presentation will be a checklist of many of these errors that can appear with some very clear systematic approaches for identifying when they might be happening. And finally, I'll try to summarize everything with 4 big ideas for avoiding bad data, looking for signatures of bad data, etc. So, to put it even more clearly, here's what I hope you'll take away from this webinar. First, I want you to be able to identify bad data. Somebody hands you a figure that has rheology data, and I want you to be a good detective to identify when to believe it and when not to believe it. Not only that, I'd like you to be the scientist about bad data, to hypothesize why the data might be bad or non-ideal. And going beyond that, I want you to use maybe the most important tool I'll talk about today, which is that on real experimental data plots, you can actually co-plot the experimental limits of the instruments that you're using. And this can help identify the region where the data may be non-ideal. And finally, of course, all of this is to achieve the much bigger perspective here and the bigger goal, which is to present good data, because that's the truth of the matter, and that's what will allow you to do whatever your job function may be, from industry to academia, etc. We try to pursue what's actually happening, not just the instrument artifacts. So how bad could the data be? I'll show you some of my own data taken with students and postdocs and things with me, but data that somehow had my fingers on it. So any bad data should be blamed on me. So here's the first set of data. This is a flow viscosity curve that's plotting the apparent shear viscosity as a function of shear rate. If something's Newtonian, it looks like a flat line on this curve. And if it's water, it's a flat line that has a viscosity around 1 millipascal seconds, around 1 on this coordinate. You can see the liquids that are on here, they're actually all water-based. They have a region where their viscosity is nearly that of water, but there are these two things on either side. On the left-hand side, you see that there's some scatter, and some of the data looks like it might be shear thinning on the left-hand side. On the right-hand side, it's kind of magical. It looks like it's shear thickening. And if you didn't know any better, you might have that very interpretation. In fact, when showing my own data to other people, that's often been the first interpretation of what's going on here. So is this non-Newtonian? The answer is no, and I'll tell you why as we go through this talk, and how to identify exactly where to stop believing the data due to different instrument limitations. The instruments are very good, but everything has limits, including these instruments. Here's another example. I take the simplest, most abundant liquid on Earth, water. And I measure this in oscillatory shear, and I report the viscoelastic moduli as a function of the frequency. What would you expect? You wouldn't expect water to have an elasticity, but that seems to be the dominant effect here. So does water really have an elastic modulus? I think if you comb the literature, you can actually find papers that claim that it does, but this is my own data. I won't point strong fingers anywhere else. Does water have an elastic modulus? And the answer is no, and I'll explain where this signature comes from and how to avoid it. It doesn't really have elasticity. There's something else going on. In this case, it's surface tension, and I'll make that clear as time goes on. How about this? This is maybe one of the most famous and popular issues that people see when doing a frequency sweep. Look at very high frequency. I'm plotting the viscoelastic moduli. This is for a biological material, a gel. Still water-based, but it is a gel, and so that plateau and G prime is true in this case. But you see at high frequency, both the elastic and the viscous modulus start increasing, and this is magical. I've found papers where people interpret this as a molecular structure of the material in order to have this frequency scaling. And it may be true that some materials have particular power law scaling at high frequencies, but what molecular structure produces this high-frequency upturn? None of them, and I will show you exactly where it does come from, and the hint is that it comes from inertia. It's an oscillatory test where you have to have accelerations, rotational accelerations, wobbling this geometry back and forth, and that ends up producing a torque that's required to oscillate, and it tends to show up at high frequency. But I'll show you ways to plot a line on this plot that identifies exactly where these features might be appearing, and give you some tips on how to look at your own data to identify when that might be the case. So here's a sneak peek at the 4 big ideas for checking the data. The first thing, as I've hinted at, is that you can co-plot boundaries on top of your data. A quick example is shown on the right. This is the same data as on the previous slide. There are 3 dotted lines that you see, and I'll give you equations for making those plots to identify different limits. Here you see the very bottom horizontal line identifies the minimum torque limit of the rotational rheometer used. Did that matter for these tests? It's getting close, but this allows you to see how close to that boundary you're actually coming. The other slanted lines are identifying 2 different types of inertia that might be going on, and we'll talk about those in detail. Number 2, you'll see, and this is something I hope you've heard from other people already, compare your measurements with 2 different geometries. If you want to be measuring intrinsic properties, you should get the exact same material functions by testing it with different geometries. I'll show you a couple examples where that's very important. Number 3, I'll show you some very good key signatures of bad data. So for example, that frequency dependence at high frequency, having a power law slope of 2, is one of the hallmarks of inertia. And you'll see why, but that's one signature to keep a lookout for. And finally, I'll show you some videos and pictures, which of course, as good as the instruments are, our eyes are sometimes even better than what the instrument is measuring, and it's good to use those senses when watching our experiments as well. So let's jump in to the first little nugget I want to discuss together to be on the same page, which is material functions. So why is rheology so hard? Rheology is so hard because we try to measure things that are very hard and very soft and everything in between. The instruments that you use, if you use rotational rheometers, have a huge dynamic range, orders of magnitude, and that makes things challenging to believe data over orders of magnitude. But across those orders of magnitude, you bump into different experimental limits. If you had a very simple instrument, you might only see one experimental limit, but this instrument is so large in its dynamic range, you bump into more than one limitation. So, moreover, the things that we tend to report in our technical reports, in our publications, when sharing data with colleagues, is not the primary measurement that we made. We make measurements of the torque and of the displacement in a rotational rheometer, but we often show them other calculations from those primary measurements. And so somehow the data gets reduced and translated, and you can sometimes lose a perspective on what these experimental limitations are. And so we'll talk about making that connection from the primary measurements to what we're actually reporting. So another comment on rheological material functions. I'd like to comment just to ask, why do we even make these measurements at all? A lot of times we'll take lots of videos and pictures in my research group, and you can tell something is rheologically complex by just bouncing the silly putty on the ground and then letting it flow between your hands. But you'd really like to be able to report that and quantify some property that is associated with what you see. So that's one big reason why we actually measure material functions. They're quantified properties that relate to things that we know are important for processing, for perception, but other things as well. So we use it to correlate with performance. In this case, this is an image from my research group showing a droplet splash impact, but the droplet's a non-Newtonian yield stress fluid, and the dynamics are different because the rheology is not simple. You might want to measure these properties to eventually choose some predictive model that you'll calibrate to the data and then make predictions, for example, computational fluid dynamics predictions in more complicated velocity fields. But many of us, of course, want some sort of microstructure insight, and by measuring these properties, we can get some conceptual model, if not a mathematical model, for what might be lurking inside of our material, or even simply just to distinguish materials, just to take it as a fingerprint. Even if you don't know what these things mean, you just know that these things might be different between two materials, and you can identify good or bad, or identify competitor versus non-competitor products. So many reasons to do this, but in all of the cases, we tend to report not the primary measurements, but calculations from the primary torque and displacement. Here's a slide on some theory for you to anchor us as well. So in all of these cases, when we report things like a viscosity, like an elastic modulus, there's always this idealized perspective in the definition that this is for a purely simple shear deformation, if it's a shear material property, which is not always the case. The velocity field may not be exactly what you think, in which case you're not really reporting a true intrinsic material property. But ideally, the velocity field is homogeneous everywhere, having the same shear rate everywhere, and only deformed in shear. And so the first equation on the top right defines the velocity field that we assume is always the case for simple shear properties when we report them. The next equation after that, the capital pi with the double underbar, this is the stress tensor that will result. So in simple shear, we expect shear stresses, but beyond that, we get other weird things like non-zero stresses appearing on the diagonal. I'm not going to talk about those stresses much at all today. I'm really going to focus on the shear properties, but I think in what we will talk about, you can see a pattern that could be matched for any material property, be it normal stress differences in shear or extensional viscosities, etc., but we'll really focus our attention on the shear stress component and the material properties from this quantity. So ideally, we want things to be simple shear and perfect. That's shown with the top image on the left. Ideally, everything's perfect, but in reality, everything's not. We try to embody that ideal in different physical experiments. You may have a sliding plate rheometer, you may have a rotational rheometer that looks like a cone, that looks like a parallel plate, or a concentric cylinder rheometer, or anything else you might dream up. In all of these cases, we're never exactly matching the ideal. Reality is a little more messy than that, and it's important to acknowledge it, especially for rheology. On the right of the slide, you see this laundry list of possible things that can go wrong, and it's kind of fun to brainstorm even more things beyond this list. In fact, if you're hypothesizing why your data may not look right, you'll be wanting to add to this list because you may have things happening that are more complicated than what is listed here. But the first thing, and we'll talk about the first couple things in some depth, is just the fundamental resolution of your instrument itself. You can only measure torque so large or so small. You can only measure displacements so small, or go to frequencies so large, etc. And that's the first thing we'll discuss. And then we'll go down the list, and I'll show you techniques for each of these things. You might look at the list right now and choose the thing that you've seen the most in your rheology data or in the people around you, just to look for it later on in the talk. So for example, item F, slip at boundaries, is something that I see incredibly commonly in the literature on yield stress fluids or dramatically shear thinning materials. We'll talk about some tips there. In that particular realm, you know that you should be using something rough to stop slip. Even that doesn't work, so you should have some way to test to make sure that what you're measuring is what you think you're measuring. So we'll have some fun with that laundry list. Before I get into that, I also want to acknowledge that these measurements have been happening for over 100 years. And if you look back in the literature, it was Isaac Newton who first decided to define the concept of a viscosity, of stresses being proportional to rates of separations, embodied in the equation on the top left. That went on, and it was first measured, this property, in 1856 in capillary flow, in pressure-driven flow, and not too long after that, concentric cylinders started to be used. So here's an image from 1890 from Couette himself. So if somebody asks, why do we call it Couette flow, here's one excuse why, although of course you can call them concentric cylinders to actually describe what's going on. Though funny that Couette's name also starts with a C, so there's some phonetic reason to connect these two things. So these measurements have been happening for many, many years, but for all of them, they've been measuring things that are not exactly the property themselves, but other primary measurements. For example, the torque in Couette's device, measured by a torsional spring, and velocity measured by actually measuring displacements and making some approximation of the derivative with respect to time. And then we try to compute something related to viscosity. So we've been doing this for well over 100 years. You'd think we would have figured this out, and of course we have to a large degree, but I hope that this talk accelerates your ability to measure good data and to report good data to avoid these common issues. This slide is a visual image to say what we measure is not what we report, and this just gives you the flow process. So we measure torques on the right-hand side. We convert that to a stress. We measure displacements shown on the left-hand side. We convert that to a strain. And then we further convert those things, usually to ratios or derivatives of those quantities, to relate to things like the viscosity. And that last equation that you see is a good one for being able to identify the experimental limits when measuring viscosity, because it's an equation that's written directly in terms of the torque that you measure and the velocity that you think you're measuring. And if you have resolution limits on either of those two quantities, you can propagate that through to the resolution that you expect for the viscosity itself. And so I encourage you, if you're ever worried about limitations, you might think about writing these equations in terms of the primary measurement variables being used to calculate what it is that you're actually reporting. So let's have some fun and go through this checklist. So the first thing relates to resolution. Here's the data set you saw to kick things off. Is this collection of fluids shear thinning and shear thickening? So I've taken the cue from the last slide, and I'm plotting viscosity versus shear rates. But the equations that you see are equations for stress, for strain, and then strain rate, which is a calculated quantity. And I'm going to write that equation for viscosity in terms of the primary measurement variable. So here's what it is. I'm using the notation of these capital F's to be a geometric factor that we use to convert between the primary measurements and the stress or the strain. And those are important in computing the viscosity. And of course, the ratio of the torque we measure, which depends on the velocity, and the velocity itself go into this computation. So if you think you have an experimental limit, for example, a minimum torque, you can plug that into the equation and compute a minimum viscosity that you can measure, or as I've written it here, it's as an inequality, that if I'm going to believe the viscosity I measure, it must be above this quantity here. It relates to a geometry factor, F sub tau on the instrument. Of course, T sub min, that's the minimum torque that has to be involved. In the denominator, I've actually recast this to be the shear rate rather than the velocity, because in this boxed, red boxed equation, you actually see I can make a plot of this equation of viscosity as a function of the shear rate, and it will look like a plot of something divided by the x-coordinate, and it should look like this on the plot. In fact, it does, and you may not be surprised to know that where that lands exactly identifies the scatter and the apparent shear thinning in the data. So if you make it your practice to always plot something like this on your data, you'll be much faster at identifying if you're near a boundary at all, and if so, you can decide if you want to believe the data on the left-hand side of the boundary or not. Certainly, that boundary doesn't mean that all of the data beyond it is bad. It just means you're missing some criteria that you've set for an experimental limitation that you want to be aware of. So the closer you are to that line, the more suspect you may become. Of course, this doesn't explain the shear thickening on the other side, but we'll get back to the shear thickening. Let me show you another set of data. This is the same biomaterial that I showed in the kickoff figures for how bad can it be, but this is a different collection of data. This is an amplitude sweep taken under oscillatory conditions. We fix the frequency, we gradually increase the amplitude of that oscillation, and we report out the apparent viscous and elastic modulus. So here the elastic modulus dominates. We're plotting the first harmonic component of the nonlinear signal. What do you see? The funny thing I want to focus on here is not what happens at large strain, although there's plenty of things to talk about at large strain amplitudes. I actually want to focus on what's happening at the smallest strain amplitudes. And what you might see is that the G double prime data, the loss modulus, looks like it's a little bit scattered, but the G prime data looks totally fine. There's actually a great way to explain why that smaller component should be scattered, but the dominant component not. If you think about the minimum torque and you compute the modulus from some torque measurement, it looks like what's shown in the red box. So any modulus looks something like the stress divided by the strain. In this case, we've converted stress to the torque multiplied by the geometric factor. And you can also plot this line as a minimum modulus that you're willing to believe, which would be associated with the minimum torque for that component. And wouldn't you know it, that line actually identifies the subdominant component as the one whose torque associated torque magnitude is below whatever the torque limit is that you're using, that I'm using to make this plot. Here I'm just taking the specification from the instrument that was used here. And you see that G prime data actually it kind of looks like it's still good, even though it's to the left of the line up there, and that's okay. Drawing that dashed line again doesn't mean all of the data to the left is bad. It just means that you're very close to or below the resolution limit, and you may expect to have some issues. Let's keep having some fun with that same material. Here's the frequency sweep that you've seen before. So let's start off by plotting the minimum torque here. So on a frequency sweep, the minimum torque doesn't appear as a sloped line with log-log slope of -1, but actually the minimum torque would look like a flat line that would be below the data here. But the more prominent feature that I pointed to earlier is actually the inertia in this system. So here's one criteria for that whatever the material is doing to resist the deformation in your instrument, that torque should be bigger than other torques required to impose the deformation, namely in this case the inertial torque required to oscillate back and forth to accelerate in rotation. So here's a very simple criteria that material torque should be larger than the inertial torque. And they scale in the following way, shown in the equation. The material torque, so now I've rewritten things a little bit differently. I want to use the material function g in my equation so I can make a plot on the plot on the right. And I'm also using gamma naught in that equation, and I'm using frequency omega in that equation, again, so that I can embody that equation on my data. So if I rearrange the equation, I get a criteria on G, that if my modulus is larger than some other criteria, I'm okay, and my material is resisting enough that it's resisting more than the inertial torque of the instrument. But if that modulus is very low, be it the viscous or the elastic modulus, if that modulus is too low, the material is not resisting that much, and the inertial torque is dominating, and you'd want to be suspicious maybe, or you'd want to look a little bit more closely at the data. So if I make a plot of this line using the geometry and the inertial parameters for my instrument, here's what it looks like. The line that's going up and to the right has a double log slope of 2, its frequency squared. Anything above or to the left of that line has a material resistance that's larger than the inertial resistance. Anything to the right or below that line says that the material is soft enough that it's not resisting as much as the inertia. Again, things to the right can be believable, but you need to be more careful in interpreting it. In fact, you see that the data does look quite believable for almost another order of magnitude in frequency until you hit that other frequency scaling. And that happens, as we'll get to, it happens because there are corrections that can be done. And even if the inertia is bigger than your material torque, you can subtract that out and calibrate that out, but that only goes so far. Eventually, even though you think you're doing a correction, you're subtracting something from a signal and you're looking for whispers inside of your signal, and eventually it's not good anymore. And so you'll still see that limit at some point. So a couple other comments on the same data. You can identify if the data is good or bad by also looking at the actual primary measurements. I glossed over that. When you're really doing an oscillatory test, you're not just measuring just the amplitude of the torque and the amplitude of the displacement. You're actually measuring oscillatory waveforms of those signals. And if you look at those oscillatory waveforms, you see in the left-hand part of the plot where the squares are, the data looks good in that the torque and the displacement are quite aligned with each other. It looks like it's predominantly an elastic material because the torque is closely following the displacement. Just like the force closely following displacement would look like an elastic spring, here torque following displacement is something that's elastic. But if you look into the point data over here, you see something very different. You see actually the torque signal looks like it's completely out of phase with the displacement signal. The better way to think about this is that the torque signal is almost exactly in phase with the acceleration. The second derivative of displacement would make it flip by 180 degrees of phase. And because it's tracking with the acceleration, acceleration is dominating. And you can subtract that out to some extent, but not completely. One other signature, other than looking at the raw data waveforms, is that you can look at something called the raw phase between the torque and the displacement. You can ask your local rheometer vendor if they provide that to you or try to find it. But if you look at that, it's the raw phase between the signals I'm showing you in these point graphs, between the torque and the displacement, not the phase that is being calculated that it thinks the material has, but the actual primary measurement raw phase. And when that raw phase jumps above 90 degrees, it says something beyond viscoelasticity is happening, something inertial is corrupting your signal. So if you look here, I actually coded my data to change from black to gray, and I changed the symbol style when my raw phase jumped dramatically. So for all of the black squares, the raw phase was 15 degrees or less. Torque and displacement are very closely aligned. And then at this critical frequency, the raw phase jumped up to greater than 130 degrees. That's another signal that inertia is important. And it also corresponds with where that dashed line is lying on the G prime data. And so these would co-locate to say from that point into higher frequencies, you need to be a little bit more cautious in interpreting your data. And this final text box just summarizes this. The thing you're looking for, again, visually here is that the raw phase, if it's greater than 90 degrees, something beyond elastic and viscous responses is happening. We're going to stick with this data set for another one. So what I want to show here is that if you do make this correction, however good your correction is, it's only good to a certain percent. Nothing is perfect, and if you make measurements, that's a creed you should always remember. Nothing is perfect. There's always some uncertainty. There's an uncertainty even in the correction. So what I've done on the data, actually, is I've plotted the equation shown in the red box, which says that the apparent modulus I would expect to see if I took my inertial torque and converted it into an apparent modulus would scale like this following equation, where epsilon represents some little bit of torque leaking into my apparent moduli signal. So that is to say, my torque and displacement may not be exactly 180 degrees. If they're a little bit off than that, I might be thinking I'm still measuring elasticity and viscosity, but it's really coming in from a torque signal that I'm not perfectly correcting. And that looks like the equation shown there. We expect that it scales like the frequency squared. This explains the signature in the data that you would see, that both of these signals look like they scale with frequency squared. And to plot that line, I'm using epsilon equals 0.01, which is to say the torque correction is great. The torque correction here, it's able to correct to within 1% of the actual inertial torque. And below that, you may not expect it to be correcting that well because you're subtracting two big numbers and trying to find the difference. But this helps explain why we can go beyond that initial limit line to be even better. To transition here, we're going to think more about inertia and inertia of our instruments. So we see inertia not just in oscillatory frequency sweeps, but we also see it in creep tests. For a creep test, of course, we're taking our sample. We theoretically think that we're imposing a step in the shear stress. What we're really imposing is a step in the torque on our instrument, or trying to approximate a step torque if I have a separated motor transducer instrument. But in the example here, I'm using a combined motor transducer instrument where I apply a torque on the moving boundary and I measure its displacement. And you see these oscillations. So I'm not asking for an oscillation, but it's giving me an oscillation. Moreover, if I look at short time scales with that inset, what I see is it looks like there's a very distinct power law region where it looks like my displacement is growing by time raised to the power 2, which is a quadratic increase in time. Where do these things come from? So at short time scales, this is actually the acceleration of the instrument itself. Before the material can resist anything, the material has to get up and the instrument has to get up and get moving. So if you've ever solved classical physics acceleration problems, F equals ma. If F is constant, your acceleration is constant, which means that your displacement will be growing like time squared initially. That's exactly what happens here. The equation that I'm showing with the dot, dot, dot just looks at the very first term that you'd expect to see, independent of what the material is. This is true even if the material is a rigid, very stiff material. The first thing you'll see is something has to get up and get accelerating. Of course, you don't see that very much if you have a very stiff material because you see the material resistance very quickly. For this soft material, or especially water-based materials, it's very easy to see that acceleration stretching over very long times. So if you're measuring creep compliance of soft materials, especially biological gels, biological materials, don't interpret anything in that initial squared region as anything elastic or viscous or anything. It's not a real material response. It's just the instrument response to accelerate. Let's also talk about the oscillations. So these oscillations happen for the same reason that a mass suspended from a spring would oscillate when you pull it down and let it go. That oscillatory frequency of a mass and spring, if you might remember from solving it, always scales like the square root of the stiffness divided by the mass. The bigger the mass, the slower it oscillates. The stiffer the spring, the faster it oscillates. So that's also happening in our system on this rotational rheometer. The mass is the rotational inertial mass of the instrument. The stiffness is the elastic stiffness of the material. If there was no elasticity, you wouldn't see any ringing, but this ringing tells us our material being tested here has some real elasticity that's causing this to oscillate like a mass on the end of a spring. When you see that data, you don't have to ditch it and kick it out necessarily. There are ways to extract useful information from that data. It's not the leading order thing you'll probably do if you're new to rheology, but if you've been doing this for a while, you might be comfortable going in and fitting other equations to the ringing to get more detailed information about your system. Let's talk more about oscillatory accelerations. So something that's not often discussed, but I've had many people ask me about as I give talks, especially to the solid mechanics community, because they love to question the assumptions of all of our equations here, is that when we do any of these tests, not just the instrument needs to accelerate, but the material itself needs to accelerate. It has an inertia, it has its density that needs to, if it's oscillating, it's going back and forth, there's the acceleration that needs to happen for that material itself. So what does this look like in a real instrument? You may remember if you've solved the mathematical problems like this, if you model real materials, if you, for example, have a slab of material and at the bottom you have a flat plate, like a jello plopped on top of a plate, and if you oscillate the plate back and forth, the jello will wobble back and forth. And what you're seeing is the density of the jello that's causing it to wobble back and forth. And if it's more stiff jello, it will wobble a little bit faster in response. What this really looks like is as you're oscillating a boundary, you're actually sending waves through a material. And if you have a very small gap between your moving boundary and your fixed boundary, you'll never notice the wave. It just looks like the shear rate that you think that you're imposing. But if your gap was very big, you would definitely see these oscillatory waves. And the animated GIF on this slide shows you something of what you'd expect. If you didn't bound the top of your material and you only had a lower bottom plate oscillating back and forth, you'd see these waves going, both due to viscosity and due to elasticity. So when is this happening in your experiment? There's a way to draw limit lines for this as well. The best criteria we take from a beautiful paper by Schrag from the 70s in the Journal of Rheology. But the concept is simple. The math is very complex, but the concept is simple. If the wavelength of that oscillating wave is very big, compared to the diameter or the gap of our measurement instrument, we can never see the wave, and it just looks like what we would ideally expect. So there's the limit given in the inequality equation, that L, the wavelength, must be much, much bigger than our measurement gap. When do you expect to see problems? Well, when your gap is big, or when L is small. But when is L small? And how much greater should it be? Actually, taking results from Schrag, if it's a factor of 10 or bigger, usually your error will be 10% or less. And if you're willing to tolerate more error, then you can soften this criteria, but this is the criteria we'll use here. How to estimate the wavelength. So I've taken the results of Schrag and I've tried to simplify it and rationalize it for you so you don't have to dig into the math. The equation is given there, but the simple scaling is down below. So the first scaling is that the wavelength should be something like the wave speed, multiplied by how much time you're taking to make an oscillation. And these are two simple concepts because you know that the wave period, shown all the way on the right, is just the period of an oscillation, 2 pi over omega. And the wave speed looks kind of like the mass on a spring frequency. It's the square root of some modulus divided by a density, which looks kind of like the square root of a stiffness divided by a mass. And you see all of that appears in the equation up above, that the wavelength of the oscillation depends something like the wave speed times the period. You can take the inequality and substitute in the results from below to make an inequality on how big your modulus should be so that it's stiff enough and the waves propagate fast enough that you never actually see the waves in the small gap of your sample. And here's that inequality. You might look at this and say, well, that 10 is arbitrary. Sure, make 10 into 100 if you want, or make 10 into 2 if you want, and it'll change the front factor. You might look at this and say, well, how do I know my phase angle? It could be anywhere, but the phase angle delta will only vary from 0 to 90 degrees, and cosine squared of delta over 2 will always be order 1. It doesn't change that much. And if you assume that's order 1, you can draw experimental limits on the data. So let's go back to the data and show what that limit line would be. And so here's the criteria that the wavelength must be at least 10 times the gap. We know the gap. It's the gap between the concentric cylinders. I can't change it, but I know what it is. And I don't know the modulus, but I know everything else, and I can actually make a plot of modulus versus frequency with the rho and the d squared as the front factor. And so you'll have problems when your frequency is high, so if you're far to the right on this plot, that's when you expect the problems to occur. And you'll have problems if your modulus is very low, because the wave speeds get very slow, and you can imagine waves building up in between your gap. So stiff materials, lower frequencies helps you avoid these sorts of issues. But if you don't want to think about all these details ever again, you might just remember this equation and plot it on your plots of modulus versus frequency to know when these problems might be occurring. In this case, it helps us know that maybe the instrument inertia effect that we thought was going on at high frequency is not the only suspect in this crime. It might also be things like the inertia of the material itself and these oscillating viscoelastic waves. Something else that's in this topic of inertia and fluid inertia, but not with oscillations, but with steady flow, is secondary flow. So in this data set, I made these measurements with a cone plate device. And so ideally, my cone is rotating, my bottom plate is fixed, and the sample in between experiences nice, simple shearing, which is true under some conditions. But if you flow really fast, I think you would believe that you can maybe make things go turbulent and make things very complicated in the flow down there. But when is that actually happening? And the best criteria for that is to use a Reynolds number. And I choose to use this criteria. There's actually a nice analytical result that says, as you're rotating the cone, way before you get to any turbulence, you start actually creating a flow that's not the simple circular streamline flow that you think. On the rotating boundary, you tend to throw material out a little bit, and so you have this secondary toroidal flow field that's superposed on what you know you want to be there. And that additional flow means additional dissipation. It means you're going to measure an additional torque. So at high velocities, your torque will be larger than you expect. By what factor? It's given by this equation to leading order, that it depends on the Reynolds number squared. So depending on your tolerance, maybe you only want up to 1% deviation due to these effects. You can identify some Reynolds number maximum that you don't want to go beyond, and you can substitute that and rearrange this into an equation that you can plot as viscosity versus shear rate, where Reynolds number is reinterpreted directly in terms of the shear rate. The Reynolds number max here I've set equal to 4.05, and if I plot that equation on this data, it identifies exactly where this increased torque effect is occurring. And so no, this is not a shear thickening material based on these measurements. Is this non-Newtonian at all? I would say within the accessible experimental range, it's Newtonian. I wouldn't be able to say anything confidently either below the low torque limit on your left or above the high Reynolds number limit on your right. And so how could you modify these boundaries? You could look back at the equations that define these boundaries, try to find some way to maybe separate them out, to lower them or to raise them. I think maybe one of the most interesting things, though, is no matter what you do, at some point these two lines will cross. So no matter how good your rheometer is, I can find some viscosity below which neither of these criteria apply, and you will either not be at a high enough torque or your Reynolds number will be too high where these things cross. It's a no man's land at low viscosity. Maybe that's why we don't measure the viscosity of air yet in our rheometers. Even water is hard enough. We've got a range of experimental accessibility of a little bit more than one order of magnitude, from about 10 to 100 inverse seconds for these conditions. Secondary flows can be caused not just by fluid inertia, but by fluid elasticity, which is a more complicated idea. But even if you didn't know that that should happen, you can still find the data through some good sleuthing and detective work. Here's some great data from Ron Larson's group on elastic instabilities. I show this data because this plots what you would be looking at from your instrument. You would be looking at viscosity, apparent viscosity, as a function of the shear rate. And if you look at any one of these curves, you see that it looks like these materials are shear thickening in some fashion. But these tests are done very nicely because the tests are done at different gaps and under different geometry conditions. And when that's done and you change the geometry, you see that the curves don't overlap, which is a great indication that something else is happening. And this apparent thickening that you see is not really an intrinsic property. And if you dig a little bit deeper, you can see where the problem occurs. So the problem occurs for big gaps. Whereas for small gaps, you tend to suppress this instability. Same thing is true with the Reynolds number instability. The smaller the gap, the more the dissipation dominates, and you can avoid some of these instabilities. And so as general detective approaches, using a different geometry can be extremely useful, and not even knowing why it's happening, but identifying that something funny is happening with your system. So let's check back in with the checklists. So those first few we spent a great deal of time on because they're important. There are several experimental limits you can co-plot directly onto data, but we maybe haven't even gotten to your favorite reason for having bad data. We haven't, for example, gotten to the slip at the boundaries, which is one of my personal favorites. The first one on this list we're going to talk about is maybe surprising and may only matter if you're measuring very low viscosity systems, but many of us tend to be doing that these days in the biological sciences, in pharmacy. Any water-based system tends to have these sort of effects. And so let me comment on how surface tension might mess up your measurements. So ideally, if you load a sample, you load it up so that the sample perfectly contacts along the circular contact line of your plate or your cone. Things are not ideal, and I've exaggerated it in the sketch on the right, but really nothing is ever ideal, and you always have some sort of deviation from your perfect rotational symmetry. And it turns out that surface tension can tug and pull on that plate in a way that actually produces a torque. And here's what some of the data looks like. So the data I'm showing here, I'm not plotting viscosity versus shear rate just yet. I'm actually plotting the primary measurements. I'm plotting torque versus velocity because the signature becomes crystal clear what's happening. So in a measurement of torque versus velocity with water, and I'm keeping it simple with water here, we see a torque plateau that happens at these very low velocities. And once the velocity is big enough, then I approach that solid line, which is the expected result for water viscosity measured in this device. The three colors that you see, black, red, and blue, were a deliberate test taken where we deliberately overfilled a little bit. So the black is our most ideal fill we could get with the perfect volume. The red, we actually added one droplet, a very tiny droplet of water, additional to the boundary, just to break the symmetry deliberately. And you see that the plateau and torque jumps up because of that. For multiple tests. There's a little bit of stochasticity in here, but the general trend is that it jumps up. For the blue, we added 2 additional drops of water for a total of 3 tiny drops of water, and the torque goes up even more. These are very small droplets of water, and I'll give you some measurements of the overfill, underfill on the coming slides. But look for a moment at how much this changes the minimum torque limit of this measurement. The bottom horizontal dashed line is the minimum torque specification on the instrument being used, and that's probably true. The instrument is good enough to measure torques all the way down. In fact, it's definitely that good because I can measure all of the surface tension effects that are actually orders of magnitude larger. But what that means is that my effective minimum torque that I can trust is actually much bigger than the specification, not because the manufacturer did anything bad, but because the sample is not loaded perfectly. And so a little bit of error jumps this torque noise floor up a couple orders of magnitude. If you didn't look at the data in torque versus velocity space, but instead as viscosity versus shear rate, it would look like this. So if my torque was constant in that low velocity range, this actually looks like a yield stress, or looks like a very shear thinning material. And this is another reason why, even with a low viscosity system, you might think you're measuring shear thinning. Even if you're above the instrument specification and it looks shear thinning, there may be other things going on. And one thing to test in this case would be to double check that your loading is perfect. You could do reproducibility studies, etc., or you can just look directly at your instrument and make sure that the fill is perfect. These issues of surface tension show up in other ways as well. For example, with the same setup but in oscillatory measurements, where we have 3 different loadings that are not different by very much. I list on the slides here the volume in microliters using a micropipette that we loaded into the instrument. So it ranges from 459 up to 495, a negligible difference even by eye, you might think. But by changing that just a little bit, you see that our ideal fill is in the middle. It's the red triangles, and the other 2 are terrible. These tell us that water has an elastic modulus, which we know to be false. And this reproducibility by changing the volume a little bit helps us to see that this is not a reproducible effect that we can really trust. How does that look on viscosity versus frequency? Dynamic viscosity, it looks again like it's sort of shear thinning because we have these plateaus in the torque. So does water have an elastic modulus? My strong argument would be no. But surface tension makes it look like it has a modulus. So how can you avoid these things? So of course, if you're measuring low viscosities, you can try to use a micropipette to get the perfect volume. You can choose geometries that are better than others at avoiding this effect. So for example, a really bad geometry would be something with a big diameter where the surface tension is contacting with its contact line at a very large moment arm, where you have a large perimeter to have a big effect. And a much better geometry would be something like a single gap concentric cylinder, a Couette device, where you filled up to the little mark on the shaft so that you actually have a small radius of contact and a small perimeter around which for the surface tension to hold. And in our publication on this, we show that that's clearly the best geometry for using a rotational rheometer to measure viscosity of water, for example. Other things happen on surfaces besides just surface tension. So if you have that water sample and you add into it something like a protein solution or some surface active agent, a surfactant, you can see even more weird behavior. So here's beautiful data taken by Vivek Sharma et al. When Vivek was in Gareth McKinley's group at MIT. And this is a great example where measurements with a cone and plate look like they're shear thinning, but they're not. And they're not because what's happening in the system is that your added polymers, your proteins that are dissolved, are actually going to the interface, making a film, and this is what looks like a yield stress shear thinning material. But if you make these same measurements of viscosity, but in an enclosed device, in a microchannel, to check these things, actually everything looks Newtonian. If you get rid of the free surface, sometimes things can be better. So I'm trying to tell you how to avoid bad data with rotational rheometers and shear. Sometimes it's good to use even other techniques like capillary viscometers, or in this case, a pressure-driven microchip viscometer. Now we get to maybe my favorite topic, which is slip, but I don't spend that much time on it. But slip is one of the most common things you see if you're dealing with structured liquids, especially dramatically shear thinning materials, especially yield stress fluids. And what are the signatures you're looking for? So many people will make measurements with a smooth and then a rough surface to make sure that they get the same or get different results. Actually, if you only do that and you measure with smooth and you measure with rough, if you see a difference, you know that there was probably slip happening in the smooth surface, but you still can't rule out slip happening on the rough surface. The best way to verify that you're actually not slipping is to make repeated measurements by changing the gap. And only when the stress and strain rates, the intrinsic measurements line up, can you believe the data. So what I'm showing with the data here is a test with Nivea lotion. So it's a lotion that doesn't feel like it has a yield stress, but it does. These instruments are delicate enough to measure that. And I'm showing two groups of data, one with sandpaper, the open symbols, and one with just the smooth surface, which is the solid symbols. And I'm showing for each of them 3 different gaps of testing. So with the open symbols, you see, at 3 different gaps, all of the measurements lie right on top of each other. And even if I never measured with the smooth, if I only had that one geometry, but everything lined up, I could be confident that I'm not having slip or other non-ideal effects in the kinematics here. But to show even more contrast and to show a signature of the bad data, if you look at the filled circles, you see that as I change the gap, the stress-strain rate curves don't totally match up. What's happening is that as you decrease the gap, the effect of slip becomes more and more important, and it looks like it's easier and easier to flow because you're not really flowing the material. And so you see these curves shifting down and to the left in this case. And so if you change the gap, and that's the direction your curves are shifting, that's a hallmark of slip in your system, and you need to do something else to avoid it. So how do you roughen the surface? You can use adhesive-backed sandpaper, which was what's used in these measurements here. You could sandblast your own plates. You could purchase sandblasted plates. They even have toothed plates and serrated plates that you can make or you can purchase. So a lot of people know that this is an issue, and we have for a very long time. But if you're new to the field, this is one of the important things to know about, that this is a key issue that you're going to want to avoid rather than embarrassing yourself in front of the other seasoned rheologists around you. So check for slip if you have a highly structured material. I talked about changing gaps to check for slip. By changing gaps, we can actually check for other effects as well. So I'm going to go back to my trustworthy standard water to make this following demonstration, where I'm showing the apparent viscosity plotted against the shear rate. And I'm testing this water sample in parallel plates at very different gaps. And this test sounds trivial. Why would you even do a test like this? Water's a little tricky to measure anyway, so it helps exaggerate some of these effects. But I also wanted to do a test here because I want to see how low of a gap I can actually use and still believe my instrument, because you may want to go to small gaps to achieve very high shear rates. Important if you have processing applications at very high shear rates. Smaller gaps access higher shear rates. It's also important if you have tribology applications, and you might want to force the gap to be small but still controlled. Or you might just want to check the parallelism of your instrument, just to see how good the manufacturer really is at making these things parallel and aligned. So in this case, we were more driven by the tribology applications and how parallel these were. And in the data that you've been looking at here, each color is a different set of data at a different gap. And the smallest gaps are open symbols, and the largest gaps are the closed symbols. So let's start at the black circles, the largest gap, which is not that large, it's 500 microns. But what you see is the hallmark of apparent shear thickening of the water, but you know what this is coming from. This is coming from Reynolds number and secondary flows giving you apparent shear thickening. As we decrease the gap, we stifle that response, and so we push out the apparent shear thickening to higher and higher shear rates, already telling us it's not a true material response. So the red pentagons, the blue diamonds, the triangles, etc., they all have that limit where their shear thickening being later and later and later. At some point, things look like water should. It looks like the viscosity is constant. But at another point, you see another deviation. As the gap gets smaller and smaller, you see that at high rates, the apparent viscosity goes down, not up. So what's happening here? Somehow, I make the gap smaller and smaller, and it looks like, or the instrument feels like this system has a lower viscosity than it actually does. So that's what I'm highlighting here. The reason for this is because when you get very close in gap, no two surfaces can ever be exactly parallel. And any finite non-parallel system is going to have a gap that's a little bit bigger than you probably think it is. Because when you zeroed your gap, even if you waited until actual contact, being non-parallel means the gap is a little larger than actually zero. So when you back off, if you're very far away, that little difference is negligible. And you'll never notice that things aren't exactly parallel. But the closer and closer and closer you get, the bigger this offset error is due to non-parallelism, and the bigger the effect is. Why does the viscosity go down? It goes down because you think the gap is almost zero, but it's actually bigger than that. So it is easier to flow than you would have expected if the gap was actually that small. So in this case, going down to 10 microns, be careful with your Peltier plates. If you take things down to 10 microns, you might scratch some of them. But in this case, that was a limit where we started to see this effect. You can actually, there's another effect here, not just the parallelism, but sometimes as you get the plates very close to zero them, there's actually another offset error where you think you've contacted because you're looking for a measurement force, but you haven't quite contacted yet. And that gap offset can be calibrated. Even the slight non-parallelism can be slightly calibrated by assuming that the gap is bigger than you thought. And what's shown on this slide is a method for calibrating this. So this is a method that's been around for 30 years now, but it works very well, and there are a couple ways to implement it. But by taking that same data of viscosity versus gap, if it's non-constant, for example, the plot on the left shows that at small gaps, the viscosity looks like it's smaller. But you know it's not really smaller. You can make a correction assuming a gap offset, and with that correction, the blue circles actually show you what you now think the viscosity is, which is much better. And if you're trusting that correction, you can go to smaller gaps and still make measurements with your liquids. The plot on the right shows you another embodiment of the exact same equation, showing you where the red line goes through the data is where we think the theory really applies, and that's how we're calibrating this offset error. There are a couple references up here for you to see other people who have used this technique in case it's relevant to you. This technique might be relevant to you if you want to test very small volumes, not just high shear rates. So I work with some biological materials where we want to go to very tiny gaps, so we don't need that much sample. And what I show here is an operational diagram that shows what range of gaps might be accessible given all of my experimental limits that we've already talked about. So I have a horizontal line labeled as number 4 here called the maximum volume limit. I need to be at a gap that's small enough that I can fit my volume into the sample, and I can of course squeeze smaller if I wanted to. If I squeeze too small, I'll get to some minimum gap where I don't trust the data anymore, and that's the below horizontal line called the small gap limit. And the other 3 lines that you see here are other limits that we've talked about. So I can't go to a velocity that's too high because the instrument only goes to a maximum velocity. I can't go to Reynolds numbers that are too high, or you'll see the secondary flow limit in the top right. And I'll still have a low torque limit for a certain viscosity of what I expect. And so this narrows in our experimental window. And the smaller your sample is and the lower its viscosity is, the more and more narrow these windows will become. But this might be a nice way to quickly check if you can actually measure your sample at the small volumes that you have. Of course, if you're a synthetic chemist and making very small samples, this may also be useful if you only have very small samples of material to be tested. Let's check back in again with our wonderful checklist of potential errors. We're almost to the end. I wonder if this is a favorite of yours of things that we haven't talked about. We haven't talked about the sample becoming non-homogeneous, so I'll show you a fun visual of that. Nor have we talked about viscous heating, nor edge fracture, and I'm sure you could brainstorm at least 3 more things that you care about or you've seen before that may not be on this list. If so, I'd be happy to take questions during the Q&A on those very things. So let me address a couple of these other issues that are not in the book chapter, but are important for this webinar to have a more complete list. The first one is viscous heating. Viscous heating, we're shearing, we know we're dissipating energy due to viscosity. That energy turns to heat. That heat usually decreases the viscosity of your system, and it might look like your system is shear thinning at high shear rates, even though it's not. And so one way to identify where viscous heating might be dominating rather than shear thinning is to compute this dimensionless group called the Name-Griffith number. I think the simplest way to think about it is as a ratio of the change in your viscosity compared to your starting viscosity. And that's what's in the first equation there, delta eta divided by eta. That's really where the definition of this number comes from, even though at the end of the day, you see that it depends on the gradient of viscosity with respect to temperature, your velocity squared, and that kappa is the thermal conductivity of your material. So if your thermal conductivity is high, if kappa is very big, it means it can get rid of the heat very quickly, which means that you're not heating up your sample much, you're not lowering the viscosity very much, and your Name number would represent that by being a smaller value. So for example, here we identified a critical Name number. We said we're maybe willing to tolerate 10% errors due to viscous heating. Therefore, we can compute a critical Name number of 0.1, and we can show that on each of these plots. Each of these plots is viscosity versus shear rate for 1, 2, 3, 4, 5, 6 different conditions that we were comparing. These were different textured surfaces with very small gaps, and we wanted to be sure that what we were seeing was actually shear thinning, not viscous heating, and lo and behold, all of these are really showing viscous heating. In any one of those plots, you see the orange dashed line. Anything to the right of that line has a velocity and therefore a Name number that's bigger than 0.1, which means that viscous heating is more than 10% important. And so the drop in viscosity that you see is actually likely due to viscous heating rather than shear thinning. How could you tweak this around? You can't change much. Changing the gap here doesn't fundamentally change your Name number. You can't change out the thermal conductivity if you're trying to test the same fluid. It's actually really tricky. What you can change is the range of velocities that you need to achieve the shear rates that you're trying to get. And that's how you can tweak the Name number to maybe be in a better range for your particular measurements. Here's another favorite of mine, which is a large amplitude oscillatory shear test. Many of us do this test to find out where the linear regime is at small amplitudes, and then we do our frequency sweep. Some of us do this test trying to get information in the nonlinear regime, and that information can be very important, especially when those conditions might be related to some processing conditions that actually occur at large amplitudes, that actually occur under transient timescales where you want to measure these types of properties. So for this, I'm showing, and I've spilled the beans here already, it looks like from the data that this is nominally a softening and thinning material. G prime and G double prime both go down as a function of the amplitude. But I'm also showing you what our other good instrument in the lab sees, which is our eyes, which is a photograph, or actually still images from a video, showing that the sample is not doing what you think it's doing, and it looks like it's shear thinning. So we've taken a video of this that we've shared on our YouTube channel that you can find, but I'll also be showing it here right now. And so I'll play the video right now for us. So here's a video taken with a macro lens to get a nice zoom in, and we started at 43% amplitude with the video that I'm showing here. And things started off looking good, but you see some things developing that are non-ideal. The sample starts squeezing out of the back left there. We've cranked up the amplitude now, as you can see. You see some slip in addition to this edge failure where we have a non-ideal edge condition. And if you just looked at the data from torque and displacement, you wouldn't be able to tell that this is happening necessarily. It looks like the material is shear thinning and softening. And in fact, the material feels a setup that is indeed softer and easier to deform because the material is leaving the gap. You have less material to deform, it's coming out of contact with the plates, and it is easier to push this material around. And this definitely is not rheology, or it's sort of rheology, but it's not a material function that you'd be reporting with a test like this. Sometimes we see 3 arms, sometimes we see more. We and some other people sometimes call this an octopus effect, where these arms just magically seem to come out and flip around. There's a pretty dynamic one. So as you see this video, keep in mind that anytime you collect or you're seeing somebody else's large amplitude oscillatory shear data, if you just see the data, you might want to ask them a little bit more to be sure that what you're seeing in the data is really real data. So what ideas might you have for proving and convincing somebody that the data is actually real? Well, you could make this measurement at 2 different gaps and show exactly where the data overlie each other, whatever data that you care about seeing, be it the first harmonics or maybe the raw oscillatory waveforms. You're going to want the stresses and strains to be exactly the same or within your tolerance for error at 2 different gaps to really believe that you're measuring intrinsic properties. Maybe you don't care about intrinsic properties and you care about slip. Be my guest. Use this sort of methodology to measure slip, but report it at 2 different gaps so you can acknowledge that there really is slip and you can maybe quantify how much slip is really happening. The sort of edge failure and slip, of course, is not uniquely limited to large amplitude oscillatory shear. You can also see this in steady shear tests, where your viscoelastic material might look like it's shear thinning, but it's not. And so we've taken another video that might be fun to discuss to see how bad things could be with this same yellow putty subjected to startup of steady shear tests. So I'll play that second video now. And so this is a startup of steady shear at 300 inverse seconds. You see slip, you see edge failure. It looks like a pastry is being made at some point where things are rolling around. That looks like it's going to be shear thinning in the data, but clearly you know that it's not. But again, how would you know? Either you look and at the end of the test you see everything went all over the place, but then you wouldn't know what shear rate this actually occurred. Either you're going to directly look at it, or you're going to ask somebody to give you data at different gaps so you can be sure that the data is really a true intrinsic property. If you'd like to have fun making these sort of measurements on your own, just to demonstrate to yourself or to colleagues, the putty we're using here is very similar to silly putty, though not exactly. You can find it for sale. It's called therapy putty. It's sold as a physical therapy aid to strengthen your hands after an injury. And you can get it in different stiffnesses, different hardnesses. You can look for the yellow one, and it'll be the same one that we're using in this demonstration right now. So using your eyes to see edge fracture is, of course, a very good way to identify something going wrong. Sometimes looking at the edge is not enough. Sometimes being able to look through your sample or inside of your sample is really what you need to see that there's a problem. Here's actually this green liquid system that I'm showing you here is the same system I used as the first example of data. I didn't say much about what that was. These are water-based suspensions with little microalgae unicellular organisms swimming around or fixated and not swimming around inside of that liquid. So these are about 10 microns in size. They are slightly negatively buoyant, so they tend to settle out just a little bit. And if you even think about that, you might already know what's coming, that if things are settling out, you can have problems with sample migration. You can't see it very easily in a cone and plate setup, except what we've done in this test is we replaced the bottom fixed plate with a glass plate, and we're looking up from below to observe the test over time. And so as you see the test evolving over time, what you see in the green circles below inside of those red boxes is that as time goes on, you see the green is no longer homogeneous. You don't see it settling towards your eyes. You see it accumulating towards the center, which is a little funny. Let me explain where that comes from. It turns out if you rotate the cone in one direction or in the other, the same effect happens, that after about 2 minutes, you see this accumulation of particles happening towards the center. So this is not a centrifugal effect necessarily. There was some hypotheses that this was the organisms swimming around and being very weird, but this is actually for organisms that are not swimming at all. They've been fixated. Things accumulate to the center for two reasons. One, because they're negatively buoyant. They do want to settle downwards. And two, in these flows, we've already talked about this effect of secondary flows, and I'm acknowledging on the top left of the slide what the Reynolds number is for this flow. The Reynolds number is 2. You might remember that the maximum Reynolds number criteria I used earlier was a Reynolds number equal to 4. So we're somewhere in that range where secondary flows are happening. And the secondary flows I mentioned are a toroidal flow that are going outward on the moving boundary. The rotating boundary kind of throws fluid outward that then comes back in near the fixed boundary. Our fixed boundary is at the bottom, so these particles that are settling down lower feel this velocity field that also has this inward component that's collecting them all near the center. There's this great paper from the early 80s that is very relevant here. This is shown at a Reynolds number of 9.6, where dye is injected, and this is a setup just like a cone and plate rheometer, but with a transparent plate on the bottom. I think this is a good call to us to take a better look inside of our material when they're being tested to really see what's going on. It'd be very difficult to make this measurement without seeing what's going on inside. The changes were very subtle. I didn't have a chance to change the gap because it was measured with a cone and plates. And so what I needed to do was look, and what we identified was that if our measurements are taken within the first 2 minutes, we were okay because we were still approximately homogeneously suspending these microalgae. So that's the end of our fun list, and I want to summarize everything by acknowledging and trying to organize these 4 big ideas that you've seen throughout all of these potential reasons to have bad data. And they're exactly what I said before: co-plotting experimental boundaries, comparing different geometries, looking for signatures of bad data or just signatures of instrument effects that are not bad, they're just not the material, and finally looking at our experiments. And what I've collected on the following slides are all of the examples that use each of these 4 techniques. So here are all of the examples we've seen today that use the technique of co-plotting the experimental boundary or the experimental limit directly onto the data of a material function versus shear rate, for example. And there are several of these given in the check marks here. For each of these, you've seen an equation that allows you to write, to plot a line on your data. I think it'd be great if we just expected everybody to always be plotting these lines on the data. It would make our jobs faster because we'd see if we're running into limits or not. The other thing, when in doubt, measure with different geometries. You've seen multiple issues that can be resolved or at least identified by making measurements with different geometries, most commonly with a parallel plate at different gaps. But it could be the difference between a cone and a concentric cylinder, but something that's two different geometries showing that the material properties and the intrinsic measures of stresses and strains rates should be exactly the same if it's really a true property. Third, I've shown you some signatures of data to look for. Maybe the most common one is that high frequency upturn of viscoelastic moduli that might start looking like frequency squared. Now you know where that comes from. But others as well, from the apparent shear thinning of viscosity, apparent shear thickening of viscosity in these two limits, et cetera, et cetera. Maybe one that I've seen most recently is the creep compliance, where the creep displacement and the creep compliance looks like it's growing like the time squared at short times. Nothing in that region can be interpreted as a material response. It's completely the instrument, and you have to wait until you're outside of that region to say anything is a material response. Finally, look at your data, find some ways to encourage yourself or the people making measurements for you to take photos and to take videos. If nothing else, it accelerates your communication. Even when the experiment is going well, you can maybe demonstrate and show what it is that's going well and how the material is responding. So I'll finish near where I started, which is to summarize the outline, but also the goals. So hopefully after this, you'll feel more equipped to identify bad data through these techniques. I hope I've also equipped you to guess why the data might look bad, because if you can identify why it's going bad, you can identify a way to avoid those issues by changing geometries or even changing a different type of instrument to use. We talked a lot about co-plotting experimental limits. And finally, at the end of the day, I want you to present good data. Don't be an example in somebody else's presentation about collecting bad data. Make sure your data is good. For many more details, you'll find it in the book chapter that I've mentioned early on and is shown in a screen grab here. Finally, I want to make some acknowledgments. The data that's here is not just a product of myself, but also many students in my research group or other people I've worked with in the past. In particular, the videos that you've seen today are from Rebecca Corman. She's fourth in from the right there in the picture, so thanks, Rebecca, for those great videos of us, for us to see what's going on. And other data was taken by other students in the group as well, and I want to make that acknowledgement. With that, I'll finish with the conclusion slides to try to encourage you to try to be better at taking good rheology data. Thanks.
Randy, thank you for that great presentation. A recorded version of this webinar will be archived and available through the TA Instruments website. We'll now begin the question and answer segment of this webinar. Please submit any questions through the Q&A window. We'll do our best to answer as many of these questions as possible.
All right, Randy, we've got a good selection of questions that are coming in through an active audience. So the first one is we've had a couple questions related to polymer melts. So most of the examples you showed were focused on fluids and biological gels. Can you comment on how the limits that you discussed or other relevant limits would apply to polymer melts, and how wide, can you comment on how wide those kind of operating ranges are for polymer melt rheology?
Sure, thanks, Dave. That's a good question. And you're right, a lot of the examples I gave were water-based, very low viscosity things. For polymer melts, of course, any material is subject to the instrument limitations, things like low torque, things like high Reynolds number. But if you look at something like the flow viscosity curve as a function of shear rates, so an example of that, if I can find a slide to remind everybody what that looked like, going back a couple slides, but you might remember the shear rate versus viscosity versus shear rate curve. I mentioned this no man's land at a very low viscosity that we can't achieve, but the higher and higher your viscosity is, the wider that experimental range is. And so if your viscosity is high enough, you're not limited any longer by the low torque or the Reynolds number limit. You're more limited by edge fracture, which was shown towards the end for something that is a polymer melt, the viscoelastic putty. And maybe you're not limited by a low torque limit on the lower end, but you might be limited limited by how low of a velocity can you measure, which wasn't commented on in here for any of these systems. If you're using a separated motor transducer instrument, then the lowest speed that you can impose sets a limit on the lowest shear rate that you can go to. If you're using a combined motor transducer instrument that's more nominally torque controlled, then your lowest velocity is more limited by your patience to measure enough displacement over enough time that you're confident in calculating a time derivative to get the slope of that curve to get a velocity.
Okay, those some good guidelines. Now there's been a couple questions on normal forces. One is you've talked about the impact that rotational inertia and inertia can have on torque measurements and therefore G prime and G double prime. Can you comment on any contribution that inertia would have if you're looking to measure normal forces?
Oh, that's a great question. I guess I don't have a very clear suggestion on what that would be, but it would certainly start changing. So it depends on if you're measuring things in steady or oscillatory and looking what to expect. I think the biggest risk would be if you're looking at steady shear data, trying to measure normal stress differences, you expect that the normal stress should grow like the velocity squared. When you change direction, it doesn't change signs. The risk there is that that's exactly how inertial stresses also grow. They grow like the velocity squared, like the Reynolds number squared, as you saw in the example with the shear loading with the torque. So I don't have any examples here. If I were to do it, that would be the biggest risk. I would still plot a Reynolds number limit because that's what's going to cause these other effects of seeing, for example, at a higher Reynolds number, it'll change the pressure field, which will change your normal force, etc. If you're looking, you really care about precise normal force measurements, you do have to worry about other things, and I'll list a couple of them here. So for one, even before you get to secondary flows, if you're rotating a fluid, to maintain those circular streamlines, you actually need a lower pressure on the inside of your liquid than on the outside. And so that actually causes a net negative pressure to be produced just to maintain the ideal flow. So why do you need a lower pressure? Even though inertia isn't that important, you still are moving little fluid particles in circular streamlines. Circular motion means there's acceleration, which means you have a net force towards the center. And that net force in a Newtonian liquid would nominally come from a pressure difference as you move through the liquid. So to get the net force inward, you need a lower pressure on the inside of all of the curves. And so if you just measure water, normal force is a function of angular velocity, or even oil, something that's highly viscous, you'll see it looks like it has a negative thrust force because of that negative pressure on the inside. So you'd have to calibrate that. There are actually good equations that exactly predict what that should be, and we've used those in our group. It's not included in the summary slides here, but we've used that to make those corrections. The other thing you have to correct for with normal forces is also surface tension. Surface tension is well known to create pressure drops across curved interfaces, and so depending on how big or small your curvature is, or in what direction it is, where the liquid meets the air, that'll also create a pressure jump. So if it bows outward, you'll get a pressure jump where you have a higher pressure on the inside of the liquid. If you're a little bit underfilled, it'll actually create a pressure drop, so you'll have a lower pressure inside of your liquid if you're slightly underfilled. So there's at least a couple comments related to normal forces there and where issues might arise and how to manage them.
Okay. Well, perfect. And in fact, your comments on surface tension lead nicely into a couple questions that we've had on the topic of surface tension, especially in rotation. So and I'll kind of give a couple threads that have come through. So one is the primary examples that you gave regarding artifacts related to surface tension were for water that has a high surface tension. So one, do you expect a similar effect with lower surface tension fluids such as organic solvents? And then two, have you considered a flooded geometry that could perhaps address potential surface tension issues, but maybe raise some other issues? And do you have any comments on whether a flooded approach might be a suitable way to address those things?
Yeah, those are fantastic questions. We asked those same questions as we were preparing that work that has been published in the Journal of Rheology. I don't know if I actually cite much of that in the slides, but it's in the book chapter cited, and we give it some very detailed treatment. So to address both of those, one, if the surface tension were different, you actually change two things. The lower surface tension means that all of the surface tension forces are, of course, smaller, but you also change the contact angle. And a lot of times with a lower surface tension, you'll have a lower contact contact angle, things will tend to be a little bit more wetting. And both of those effects come to play. And in general, yes, as the surface tension is lower and it's more wetting on the geometry, it will tend to be better. Actually, there's a nice example of that if I go to the second part of the question, which is about flooding. In that paper, we actually, and I don't, maybe it didn't come across clearly in this presentation, but the best geometry to use would be something that's a bit like a flooded geometry. If you think about a single gap concentric cylinder where you have a bob that's submerged, the ideal fill, or what's suggested by the German standard for this, is to fill it up to a little marking line that's on the TA Instruments rotational bobs, where you fill it up to a line that's above the top of the large part of the bob. And by overfilling this way, it's a bit like you're flooded, but you will always have a liquid solid vapor contact line. Now in this case, if you have a perfectly wetting liquid with a very low surface tension, because if it were ideally perfectly wetting, all of the surface tension forces would actually point downward rather than having some horizontal component. And you need the horizontal component to create the torque that we measure in these examples. So the overflooding is good. The best geometry we found to use is that single gap cuvette, where you're flooded, but you'll still contact the shaft and you'll still have some contact line. And then the lower the surface tension, the lower the contact angle, the better things will be.
Okay, good. And then you suggested that people might brainstorm other experimental errors or sources of error. And, one that is suggested is the human-related bad generated errors, such as what you might see by a gauge R&R. Can you comment on that? How should we consider it? What would you expect, or any sense for what the root causes of the operator error would be?
Operator error. I would love to brainstorm the many different types of operator error that might cause this. There are things that actually TA Instruments has tried to address themselves with, for example, the smart swap geometry, where they try to omit any possible errors of typing in the wrong geometry factors. So there's one thing that's been addressed by just engineering the setup to automatically recognize what geometry is actually attached. What else? Gosh, this is kind of a gray area that probably depends on your operator and what you think they may or may not be doing with the data. It's hard for me to think of exactly what goes on. I mean, if they fall asleep and they didn't look to see that at high velocities, all of your material was flung out, and then they woke up and never mentioned it to you, I think that you could still ask for similar things that I mentioned during the talk today, things like making the measurement at a couple different gaps, or just repeating the measurement, of course. But really, the making measurements with two different geometries is by far the best way, independent of what the problem is, to see if what you have is really a true intrinsic property that you're measuring in the results.
Yeah, I guess I'd certainly offer, in my own experience, you commented on the importance of underfilling versus overfilling, and that's probably one of the most difficult and yet necessarily manual steps of the process, and certainly a place where error and spreads in the data can appear. So, that's right.
That's right.
I think based on time, we have time for just one more question, and that last question is on one of your favorite topics of slip. And is it possible to avoid or at least reduce the impacts of slip by using it says slow, but maybe a slow application or a low torque value and a cone if you're trying to measure gels?
Let's see. It kind of depends on the gel, because there are two flavors of gel. The flavor where it's kind of a weak, hard gel, where it doesn't really flow, like gelatin fractures, but it doesn't stick back together again. And then there are soft, reversible gels, like the gels that are in hand sanitizer becomes with its additives, or aloe gel. If you go to low torques, there's some awareness in the literature that you can still be slipping, because if you think about a very thin layer of the solvent that's nearby the geometry boundary, just being at a low value doesn't necessarily avoid the slip issue. So no, not necessarily. The low torque doesn't always help. It might help. There are some cases where the slip doesn't occur until a critical value of the torque or the local stress, and so you can potentially avoid it. So it depends what you're trying to measure. If you're trying to measure, say, linear viscoelastic properties of a stiff gel, then definitely being at those lower torque values, lower displacement values, does allow you to make those measurements before slipping. So for example, if you picture gelatin again being in the rheometer, and you have, even if you have smooth plates but it's sticking well enough, you might be able to get away with measuring in the linear viscoelastic regime at suitably low torque values before slipping. So I hope that answers something. It's hard to have a very detailed interaction with the questions, but I appreciate people submitting them. It makes it more interesting here to have a little bit of an exchange, as limited as it may be, and really appreciate you taking the time to listen to the ideas that are in the talk, and I hope that really we're all in this together trying to take very good data. So I'm glad to be a part of that with all of you, and look forward to seeing all of your good data if we happen to cross paths in the future.
Perfect. Thanks, Randy. So this concludes today's program. Randy, I'd like to thank you once again for joining us today, and I'd especially like to thank all of you and our audience for spending some of your day with us. There have been a lot of questions about the availability of these slides, and I'll remind you that this webinar, like all the TA webinars, will be archived, and it'll be available through the TA Instruments site, including the video and spoken comments that go along with it. So please look forward to that, and also look out for invitations to other future webinars from TA Instruments, including an upcoming practical training series on thermogravimetric analysis, or TGA. Thank you all, and have a great day.